So we're first talking about my subject, which is close binaries. I work with eclipsing binary stars that regularly eclipse each other, and you'll know all about that in a few minutes here as we go through our talk. In creation time cosmologies, particularly Humphreys and Hartnett, one of the major questions is, yes, we know that the Earth, because of the Genesis count, that the Earth and the record, the historical records and so forth, we know that the Earth is somewhere between 7 and 10,000 years, depending on if you think there are gaps in the record or whatever. But you can't put billions of years in. You can't put millions of years in. You might stick 1,000 years here or there, but you're not going to get fantastic ages like the astronomers talk about. So we know what our age is, but what kind of age should we accept about these distant objects? What is the apparent age that characterizes the universe? Now, ESO has come out with their Planck spacecraft and has told us, we've got very accurate, notice the number of decimal places here, right there, right? They're up to 3 decimal places now. But anyway, 13.819 gigayears is the age of the universe, according to these guys, according to cosmic background radiation, and so forth. Okay. Do we just accept that and say, okay, we're 7,000 years, but 13.819 gigayears have passed? And I say, no. And I was sitting in a astrophysics class one day and learning about how stars evolve. And we're actually running the code that they use to come up with these ages and so forth. And somewhere along the way, the professor, who, by the way, I saw this professor at the mask meeting, which was only a few months ago, and saw what he's doing. But anyway, he said that, we just have to make an assumption here. We have to put a condition in here, and that is that the age of the sun is 4.57 billion years old. And so that's the assumption. I thought, well, they just knew the science. I mean, they should know how long it takes for nuclear processes to take place in stars and the different elements and so forth. But the answer is they don't really know that well. Does anybody know where they get that from? They get that from primordial meteorites, okay, the oldest meteorites. And they say they're from the solar system, so they must be, the universe must be that old. I call this the solar age condition. And this condition, this boundary condition, is stuck into almost every astronomy dating system there is. And that's why ages are astronomical. If you can get the joke. You know, I say people always say, that's astronomical, right? Okay. Well, that's the reason why. Now you know why things are astronomical, because of that number. So what I thought was, well, let's find some other time clock. Let's find another natural chronometer like Humphreys used in his spiral wind-up thing. The spiral galaxies are winding up, and they can't stay spiral galaxies very long because they just lose their spiralness, okay? So there's a clock there, and he asked me if that was a good clock, and his helium diffusion rates he did with the RATE project, okay? So what we're seeking is natural reference clocks, what I call NRCs, things that nobody can argue about. Natural reference clock, like orbits. Okay, everybody knows Kepler's laws and how fast things orbit and so forth. Speed of light is real constant and so forth. So anything that's well-founded, let's use that to measure time, okay, and get some reasonable time systems. Okay, so our first study here is on what I call geochronology, what has been called geochronology, which has to do with angular momentum loss. So I'll kind of talk about that a little bit and show you what the idea is. Basically what happens is this is a binary system, 2 stars orbiting around each other, and this is a stream, very common in algal type systems, where the stream goes and strikes the other star actually, okay? You have a gas stream there. It's orbiting around rapidly. All right, angular momentum loss, or you could call it spin. What happens over time to solar kind of stars is that single stars, they start out spinning fast, and they slowly spin down, okay? Binary stars do the same thing. They spin around. Here's 2 stars here. By the way, these black things are sunspots, star spots, okay? And you can tell a solar-type star because they have star spots. They're magnetic, okay? And so anyway, this magnetism is really important. All right, so they have a bipolar field, or like the Earth does, a north pole and a south pole. And here are these field lines that go around, and you could play with the magnet, and you could put some pins or whatever, metal fragments, and they'll create these field lines. You can see these field lines. Maybe you play with this sort of stuff, but there's a north pole and a south pole. And these are important because plasmas, as they fire off the surface, solar wind, as they fire off the surface, they travel out on these lines of force, okay? So here's a more simple picture of this. So we've got a single star here, and it has a north pole and a south pole, and coming out of this is a plasma, a set of charged particles, and they're streaming out from the star. Okay, this is stiff out to a certain place called they're called the Alfvén radius, but that doesn't matter to you. But it's out to about 50 radii. They're stiff. They go out. And what's happening? The star is spinning around, okay, and carrying those things. So these plasma particles, protons, most of them, are traveling out along these lines of force. And what happens is, as they go away, larger and larger radius, what happens is the star spins down. And so the star will spin down, starting out as a fast rotating star, and then it will slowly spin down, having angular momentum loss, or the spin loss. What happens is they end up with a nice, quiet, rotating star like our sun, okay? And so it spins down, okay? It slows down. And the spots also decrease in size like you see on our sun, okay? The field is not as strong and not as much magnetism. Okay, so I downloaded this little picture here. I put the speed skater kind of backwards. The idea is, let's start him out with his hands in, and he's spinning, and as he puts his arms out, what happens? He slows down. In fact, you usually see them catch themselves and stop at that point or something. And so the idea is the charged particles are going out and spinning. As they go out, it torques the star, so the star slows down, okay? And so it doesn't stop, but it does slow down. For binary stars, what happens? You have these magnetic fields going out, and actually of both stars. I just put it on one star to keep things simple. You have angular momentum loss, and what happens to a binary star is it slowly coalesces. It slowly comes together. And so it starts coming together and makes a contact binary. Okay, stars, the actual atmospheres are in contact, okay? And there are just all kinds of distortions there because of centrifugal and Coriolis forces and stuff. And finally, they will come together and make a single star. Okay, a fast rotating star. They call these stars FK Come stars. There also are a lot of A-type stars that spin very, very rapidly. And they think that they're from binaries. Now, one of the evidences for that is old clusters. Now, this is called the HR diagram. All I need to tell you, though, this is the brightness and this is the color or temperature. And if you plot all the stars in the sky on this diagram, they end up making what's called a main sequence, okay? They follow along a main line here, the brighter, the hotter, okay? And the less bright, the cooler. That's down here. All right, so they will follow that. As the stars get old, they slowly peel away from the main sequence. And now this is the new line here. This is billions of years later, according to their chronology, okay? And what happens is there's a bunch of stars still sitting here. And they're called blue stragglers. And they think, sometimes I call these born-again stars. And what they think they are is these binaries that have collapsed upon each other. And they're spinning fast and they act like brand new stars. And so there they are on the main sequence again. And here is a cluster. Can you pick out the blue stragglers? They are really blue. See the blue ones in there? They're not supposed to, this is an old cluster. They're not supposed to have young blue stars there. But they're sitting there merrily enjoying life, and they're these blue stragglers, and they're probably collapsed stars that have been reborn, okay? All right, how that binary mergers here. All right, so how long does this take? Okay, the evolutionist, my friend Bradstreet, who does a lot of work and stuff, he's a old Earth kind of a guy. He does believe in God, but I think he's a big banger. But anyway, on this little plot here, what he shows is a particular kind of star with one solar mass and a 0.74 mass. This is a binary star, and it shows how long they take to spin down. This is 5 days. The initial period is 5 days, so it's slowly moving binary, kind of separated. And then what happens, it spins down and becomes a contact binary. This is a contact line here, when it's only a third of a day period, so it's during contact. And this takes over what? You see that number there? That's 10 billion years. And it takes a long time for that to happen, and that's because of the SAC condition, okay? The solar age condition that's been stuffed in there. And so you end up with these big numbers. The velocity rotation goes as the inverse time, but see this huge number here, 10 to the 10th, okay? And that's because of our friend the sun is so old. And so these contact binaries are thought to be the granddaddies of the universe. They're very, very old. And here's another picture that shows the same sort of thing, more graphically. It shows two stars separated here. This is the little black area, is the actual stars. And for you science guys, this is the Roche lobes. But anyway, they slowly come together, finally they come in contact. And this little strip here takes 4 gigayears. That means 4 billion years to go from here to here. And then they slowly become a single star. So again, this shows the same kind of thing. This adds another couple billion years to go from here to here. And so we end up, this is 6 billion years worth of time to go from what, about 3.4 days, okay. And these stars are thought to start out fairly close together. That means that they might be several Earth-Sun distances apart at the beginning, and they slowly merge and come closer together. All right, so to make a big jump, this is a table of my research for 25 years, and all these guys are undergoing, they're all solar types, and they're all undergoing this coalescence stuff. Here's the period they have right now, if I can point to it here. Let me use my pointer here, okay. All right, so here's the periods now, and these negatives all tell you that the period is changing with time. It's decreasing, okay. Now you can use these numbers that I've calculated here, and this is actually making a bunch of observations, and I'll show you a picture in a few minutes to show you how I come up with these. And what I'm trying to do is come up with an NRC, an alternate clock here, because I can measure time. So I got a rate. That's all I need is a rate, okay? And I can come up with an age. Okay, so here's the period now. They're all short period. This is 0.39 days. And so here is an example of one of these guys as the period is decreasing. This is called an O minus C, or residual plot. But all you need to know is that if it curves like that if it's downturning like that, that means the period is decreasing. And so you can see over 50,000 orbits here, that even from the original starting data, it was way off down here. And we had a lot of data in these last 25,000 orbits. And this is taken in real time. And this is during your lifetime, okay? These are years, not billions of years, okay? And you can see it changing, okay? And you can see it decreasing in period, okay? And so something's up here. This is not taking, I can see this happen. I'm not saying billions of years take place here. So here's my final result. This is really jumping through a lot of stuff. And if you start out with the 5-day initial period, Here are the ages you come up with. The average age is 330,000 years. Now you say, that's a long time, 330,000 years. But that's nothing compared to 14 billion years, or whatever we're supposed to accept for the age of the universe. I mean, that's 14 billion and 330,000 is nothing, okay? Anyway, so this is a big difference here. If you start with an 8-day period, it takes longer. Start with a 10-day period, I was going to kind of have a long starting period just to see how long it would be. You're still under 1 million years there for the average, okay? And you do have some that were really fast, okay? And so anyway, so this is the idea here of this thing. And so the actual determination of the rate of angular momentum loss decreases the age of short period binaries so much, it's just amazing. So instead of having a 10 to the 10 year object, you've got objects that are thousands of years. Okay, now, you don't know where they start at. That's a problem, right? And you can take observers' estimates and so forth that it's maybe 5 days, which is what a lot of astronomers say, where these close binaries start out at. And so we're just guessing there. You can have them shorter and shorter periods and make it happen in your regular 7,000 years if you want. But the apparent ages average from 300 to 7,000 years, and it actually includes ages as low as hundreds of years for the ages of these stars. And the range easily includes the biblical age of the solar system, 7,000 years, depending on initial created periods. Now, it is possible that these objects are actually telling us that things are only thousands of years old and not billions of years old. Okay, it's more than possible. It's most likely that's what's going on. Now, all these objects here, all these stars are not cosmological, which means they're not very, very, very far away. They're only hundreds and maybe up to 1,000 or so light years away, and so they're nearby. And so it could be that these objects are telling us that everything close by the earth basically follows a biblical frame, and it was inside of this timeless region or whatever when things were happening out in the universe. So it could be that all these nearby objects, if you want to call that nearby, 1,000 light years away or more. But anyway, if you want to call that nearby, these nearby objects could be in the very young age frame of our solar system and of our Earth. And it depends on where you start the periods off of these binaries. There's lots of evidence that Jupiter and the moons and other objects, Saturn, Neptune, and so forth, are young, very young objects, and they are within the biblical ages that we normally accept, that we normally read. And so it's possible that everything here does fit in that 10,000 years kind of frame. By the way, all our professors at Bob Jones University are all young Earth creationists, and they all ascribe to things being 10,000 years or younger of age. And but yet, the universe does function. Real astronomy is going on. It has happened. And so we can do science on the stars. This confirms however way you want to take it. If you want to take it in a time-dilated format, or if you want to take it in the simple 7,000 year kind of age format, this confirms the youthful age of the universe. For in 6 days the Lord made heaven and earth, the sea, and all them is, and rested the seventh day. Wherefore the Lord blessed the Sabbath day and hallowed it, a 7-day creation. So this is just a review here. Again, we're talking about what is the maximum age of the apparent and maximum age of the universe, and the idea of the SAC condition, and looking for alternate chronometers. And if you came in late, I'm looking at finding standard clocks, or what I call them natural reference clocks, NRCs, to measure a time that nobody can disagree with. The other day I ran across information about a pulsar, which are supposed to be at the center of supernovas, and from supernovas, you can watch the gas as it expands. I mean, you can't see it happen, but you can see it expand. So I thought, aha, here's another clock. So let's go back and take those back to when they blew up, and you get a time for the supernova explosion. And guess what? The pulsar ages are wrong, and they're wrong by a lot. All right, this is a sideways view of our galaxy. Where is the ICM in the globular clusters? Intercluster media. The dust and the gas, intercluster media in the globular clusters, because that's the question there, and we're going to look at that problem. Okay, our galaxy, if you put it on the edge, it's a spiral galaxy. Maybe it looks something like this. Spiral galaxy on the edge like this. If you look at it, it has a hub in the middle, and the arms are out here. The spiral arms are out there. But around it, there is a swarm of, they look like bees or something, right? A swarm of something. What are those? Those are globular clusters. A lot of times you look at galaxies and you think, those are stars. No, you can't see stars at this distance. Those are conglomerations of hundreds of thousands of stars in tight knots called globular clusters, and they swarm around in an area called the halo of our galaxy, okay? And they orbit around. And here are some globular clusters and what they look like. This is Omega Centauri. You can see this out in the fall, low in the sky. It's a southern object, and it's huge, Omega Centauri. You can look up and find the specks. It's about as big as the moon in the sky, and just a huge, beautiful thing. But now the closest we can do in the northern hemisphere is M13. M13 is a beautiful cluster, but doesn't match up with Omega Centauri. I'm sorry. But it looks pretty cool. Even in a 4 to 6 inch telescope, you can see this, and you start seeing the single stars, and it looks very, very cool. And this is how to find it. If you go and look at Hercules, okay, in the Hercules, there is this little group of 4 stars, and this is called the keystone, all right? And if you look in the back end of the keystone, kind of in the middle, you can get that close with your finder scope, and you'll find M13, okay? It's easy to find, and it's a beautiful thing to look at. You should stare at it for a little bit so the stars start popping out and kind of look. They say to use averted vision. That means kind of look around the sides of it, and that helps you. Your rods can pick up fainter things. So you kind of look around the edges of the field, and these other stars will start. They're not stars. Yeah, they all start. These are actual stars here, and they'll start popping out, and you start seeing these things. Anyway, that's M13. All right, globular clusters are spherical-shaped assemblies of just thousands and thousands of stars, upwards to millions of stars. And just to make things simple, these stars are supposed to be very old. They're red-looking, high velocity. There are some blue stragglers in there, like I mentioned before on that other slide. They have high inclination orbits. That means they're very inclined. They don't lie in the plane. I'll show you a picture of that in just a minute. They are high eccentricity halo objects, and they have what's called low metallicity. That means very little bit of dust and gas in them. And that's what's called population 2 objects. Population 2 objects orbit in halos around the galaxy. This is a galaxy on edge, and the orbits are swinging out wide, high eccentricity, high inclination, which means they're up from 0 degrees would be in the plane of the galaxy, like these guys. Population 1 objects, like the sun, are in these circular orbits going around the center of the galaxy. Okay, so there's a lot of different little ways of classifying Pop 1 and Pop 2 objects, Pop 1 and Pop 2 stars, and these globular clusters are Pop 2, and they're supposed to be very old objects. Globular, you can kind of drop this thing out. There are some galaxies, they're called companion galaxies, smaller galaxies, in orbit around the larger ones, and they act like these globular clusters, so I'm kind of dropping those out right now. Globular clusters should accumulate dust and gas, and I'm calling it intercluster media, ICM, from steady stellar winds and outflows of the included stars. I mean, stars inside of these globular clusters, talking about the globular clusters, should be throwing out dust, okay, and gas as they emit. There's a type of star called an AGB star, which dumps like 90% of its atmosphere out into space, okay? And these kind of old stars are in these clusters, and so they should be dumping out all kinds of dust and gas. But the problem is that when you actually look at these things, they have very low levels of dust and gas, almost no dust and gas. And that tells you something's wrong here, right? Something's wrong. And so the question is, what happened to the ICM? Where is it? Where did it go? Is there somebody vacuuming it up or something? Where does it go? You know, we have a very clean housewife there or something. But anyway, what's happening there? All right, one hypothesized mechanism is that every time these clusters go through the plane of the galaxy, there is ram pressure that cleans them out. So when they come out on the other side, they're clean. Okay, so they think every time they pass through the galaxy as they orbit around, that's where they're losing their ICM. Now the thing is, though, it takes this is Newtonian orbits here, and it takes a long time. These are huge orbits. It takes a long time for them to go around, and it takes something like between 10 to the 8th, 100 million to a billion years for them to make a half orbit, for them to get back go into actually a little more than a half orbit, but to get back going through the plane of the galaxy, okay? And so during that time, they should be throwing out, the stars should be throwing all this dust and gas out, and it should be accumulating anyway. And Spitzer observations, this was in a recent Astronomical Journal article, says that the dust mass is 1/10 to 1/100th of what it should be. 1/10 to 1/100th of how much there should be. Where is it at? And it wouldn't be a population 2 object if it had all this dust and gas, because that's not what population 2 objects have. And so this is a very strange problem. Globular clusters crossing into the galaxy, plane of the galaxy are too far and few between, during which they should accumulate dust and gas from steady stellar winds and outflows. And so we have an anomalous kind of object. We should have a population 2 object that's supposed to have no dust and gas, but it should have a lot of dust and gas. So it just doesn't make sense. It doesn't tie together. So how do you get all these globular clusters clear of their dust and gas? Okay, what is my time clock here? Anybody guess what is my time clock here I'm using? Well, I'm talking about orbits, right? Okay? And we know you give a certain mass, a certain radii, you can tell what the orbital time is. The old Kepler law is p squared is equal to a cubed. Period of the orbit, a is the size of the orbit, okay? And so you can get these numbers, and we can easily calculate how long it's supposed to take. All right? And so the ICM is 1/10 to 1/100th the amount expected. But plane crossings average 10 to the 8 to 10 to the 9 years. Now, even I can make a calculation from that, and you can make a calculation from that. How old are these things supposed to be? So the time limit is some 1 million to 100 million years. And that's if you start out with everything dustless, you end up with these kind of numbers. That does not fit. Galaxies and globular clusters and so forth are supposed to be over 10 billion years old. Now, I'm not very, you don't have to be really smart to think there's a big difference between 1 million years and 10 billion years, right? It doesn't make sense. It doesn't hold together time-wise. Now, so even in a time-dilated universe, it doesn't fit the secular worldview. So we don't have to accept those billions of years. All right, so this was a problem. This is from a journal, so they're trying to solve this problem, okay? So they got to figure out something here to make this work. All right, so their explanation is, Well, in these clusters must be classical novae. Classical novae are stars that are binaries, and basically have a white dwarf and a giant here. What's happening is a little stream of gas comes down, and it makes a disk, and the disk slowly falls onto the tiny white dwarf, and the white dwarf is really compact and heavy and so forth, but it's small. And so what happens is the gas slowly will come and actually feed onto the star and actually create an atmosphere on these stars. White dwarfs, by the way, are basically cores of dead stars is what they are. They're just a core. But you give it an atmosphere, and then the atmosphere will do what? It'll compress, and boom! You have a nuclear explosion. And so the nuclear explosion, this is the explosion going out, boom, the explosion, and that's going to blow everything out of the cluster, right? Okay, well, let's look at this idea. Maybe that's the answer, okay? There's all kinds of these. And so that's what they did. These guys, let's see, their names are Moore and Bildstein. Moore and Bildstein guessed at what rate these things are blowing off and stuff. But when you do the numbers, when you actually try to look at everything and how many stars there are, how many of these objects there are actually there, you still have problems. The study shows that more massive clusters still have a clearing problem. They don't get clear due to these runaway accumulations between nova outbursts. Okay, so they're not beat yet. So I say, okay, maybe just plain old novas weren't enough. Let's have supernovas. Okay, and so they started to theorize maybe there's supernovas in these, and when they blow up, they're going to blow everything out, and that'll take care of the problem. However, the problem is you go back and look at the archival records, the studies that have been done, and there has not been one single supernova happen in a globular cluster. They don't happen. They're not there. And so, just from the observations, the things just don't work out for these guys. I'm sorry. It just doesn't happen. A simpler explanation is, can you come up with a simpler explanation? The globular clusters just aren't old. And they haven't had time to accumulate the dust and the gas, right? And that is just a simple explanation. It makes sense. They would never come up with that explanation because they have to have their billions of years. So it doesn't work. And so, is the missing ICM a problem? The answer is no. It's not a problem. Because there hasn't been enough time gone by for these things to have accumulated dust and gas. And it confirms the young Earth age, and even in a time-dilated universe, even if you'd like to say that there's almost no dust, so we can just have things 7,000 years old if you want, and these are young Earth kind of objects too. For in the 6 days the Lord made heaven and earth and the sea and all that in them is, and He rested the seventh day. Now there are lots of these phenomena, and I'm tracking them down one by one, and I'd like to be able to share them with you. And where is the ICM in the globular clusters? What's the answer? It never was there in the first place. And it's not there yet.